My name is Sébastien Henry. I'm a PhD candidate at EPFL in Switzerland. And today I'm going to show you some results on the delays in time-varying networks. We study here time-varying networks. So what do we mean by that? So to illustrate a bit, I show a very simple example. Just one Wi-Fi link, two nodes with no other transmission around. And what I show here is on a 25-second Wi-Fi trace, the physical rates of every packet. So for every packet, I just store the modulation and coding scheme index, and I show this on a 25-second trace. And what we see clearly is variations, of course, but what's interesting to note is that it actually varies between some discrete sets, here mostly 4 and 2 dominant areas, and the transitions are not random. Typically, the packets stay in one MCS for some time and then jumps to another state. And what we want to study here is how do these varying rates affect the delays. And so we come up with a simple queuing model with the packets arriving from the application at an exponential rate and filling up a queue and being sent at an exponential rate. And here we assume that the rates varies between two states, a high rate state and a low rate state. And the transitions between the two states happen exponentially. And this is a model that can be useful, so as I said, to model these Wi-Fi rates, but you can imagine that it models also the case where two users are contending. So for example, if Alice is downloading some large file or streaming some video, and Bob is browsing the internet, for example, and if we look at the rate that Alice gets, when she is the only one transmitting, she's the only one using the medium, she gets a high rate. And when Bob is using the medium as well because he's downloading a web page, then Alice gets a lower rate. And this could also be used to model, for example, data center servers where you alternate between low load and high load states. And here we're in particular interested in the case where Alice has two technologies. So here this can be, for example, Wi-Fi and 4G. And of course, these two technologies have different parameters, different service rates and different transition rates. So here I show with Wi-Fi and 4G, but this could be Wi-Fi and power line communication, Wi-Fi, even two different Wi-Fi channels. And actually, this is the case that we will mostly look at for our experiment, where Alice has two different Wi-Fi channels. Okay, and we study this scenario in two different settings. A single pass setting, where Alice wants to use only one, but she wants to choose the best one with respect to delay. So the technology that offers the smallest delays. And in the second setting, she does multipass, so she uses the two technologies simultaneously. Okay, so in both settings, this is the model that we use, and at first glance, it sounds like a model that is not that complicated. I mean, it's exponential arrivals, exponential rates. It's almost an MMO, a very simple MM1 queue. The only difference is that you have now these two alternating rates with exponential transitions. But still, it sounds simple, and actually there is an explicit expression for that, for the delay. The only problem is that it looks like that. And these are only the first lines of the expression for the delay. There are actually dozens of lines like that. And this is actually why it has not been studied that much. This is a simple model, but actually there has not been that much work on it because it's like the explicit expression of the delay is really complex. And here what we want to do is to be able to say some general results on the delay in this kind of models. So we start with a single pass model where Alice wants to choose the best of two technologies with respect to delays. So this is the formula for the average rate, the average service rate. And here, okay, if one technology has a higher service rate, a higher average service rate than the other, well, Alice most likely will use this technology. So here, what we assume is that the two technologies have the same service rate. And we also do a second assumption, which is that the transition rates are similar in the two technologies, meaning that the sum of the two transition rates in the high state and low state are the same. And what we want to study is the impact of the variance of the service rate. So this is the formula for the variance of the service rate. And intuitively, what we were expecting when we started to look at that was that the higher variance will yield higher delays. And this is what we wanted to show, and we almost show it, actually. What we show is that if one technology has smaller delays for all arrival rates, then necessarily it is the technology that has the smaller variance of the service rate. So the proof is somewhat technical. I mean, you have seen the expression. But this is somehow the intuitive result that you expect, is that larger variance yield larger delays. But here what is important is that it is the case if one technology has smaller delays for all arrival rates. And actually the second result that we show is that this is not always the case. For some parameters of the service rate and the transition rate, the best technology is not always the same for all arrival rates. And the second result that we show is that for some parameters, so sometimes, the technology with the smaller delays is actually the technology with the higher variance. And this is something that we didn't expect, and that is somewhat counterintuitive. And we want to show experiments to see that it's not only a theoretical result, it can also happen in reality. And so we do a test-bed experiment. Yeah.
Do you mind going back to your model? I just want to make sure that I understand the model correctly.
Yeah.
So there are two technologies, you're saying. So there are essentially two possible choices.
Yeah.
Okay, and you're right now fixing the average service rate of both to be the same.
Yeah.
Okay, and then what do you mean if there is a higher delay in one versus another? You're fixing the variance the same, or they're not fixing the variance the same?
No, the variance is not the same.
Okay.
That's actually what
okay,
we
so
want
the
to
variance
study.
is different.
The variance is different
for each of the technologies.
for each of the. So here you have the two technologies. They have the same average service rate, but they might have different variance because they might have different high and low rate. So the mu H and mu L might be different. Only the average is the same.
But you have different arrivals that are going into each one, or is there a splitting that's happening?
No, for now there is no splitting. For now we just look at, okay, what happens in one case and what happens in the other case.
Okay.
And then I will talk about the splitting.
Okay, so what you're saying is that even when you have the same arrivals going into each one, the one with the higher variance need not give you higher delay.
Exactly.
That's interesting.
And that's the experimental result that I will show now with two technologies. So here, I mean, thanks for clarifying. It's really two different. We use one technology only at one time, and we look at the same arrival rate. And this is achieved by setting different modulation and coding scheme indices. So we want to have a controlled experiment. And what we get is something like that. So let me explain a bit what we show here. So for each arrival rate, we do one experiment with the first technology and one for the second. And we look at the delays with this technology. And we show here the difference between the delay obtained with technology 1 and the delay obtained with technology 2. Which means that in the top half of the figure, technology 1 has larger delays, and in the bottom half, technology 1 has smaller delays. And here, with the parameters that we use, so we use different parameters for the two technology, and with these parameters, technology 1 has the smaller variance. And in blue, I show the analytical delay difference. And in orange, this is what we get experimentally. And we see that in both cases, up to something like 32, 35 megabit per second, technology 1 that has a smaller variance has actually the larger delays.
How different are the variances?
I don't remember, but it's something like 1.5. One is 1.5 higher than the other, something like that. And here, at 22 something megabit per second, the delay difference is actually quite significant. This is around 9 milliseconds versus around 3 milliseconds. Okay, so to sum up this part on single pass, we have seen that variances, as can be expected, important, but actually sometimes for some parameters, larger variance can yield smaller delays, which is kind of counterintuitive. And now I move to the second setting, when we do multipass. So packets still arrive at some arrival rate lambda, but now they're split with some probability p, they are sent to technology 1, and probability 1 minus p to technology 2. And now I do not assume anymore that the average service rate are different, are the same. They can be different. And what we want to study is the impact of this splitting probability p on the delay, and we want to find the optimal splitting probability, the one that yields the smallest delays, and we want to study the impact that it has on the delays. So first of all, what is the optimal splitting probability? So first of all, if I ask you which splitting probability you would use, what you would do is use the weighted average of the service rate. So if one technology has a service rate of, let's say, 30 megabits per second on average, and the other technology has an average service rate of 10 megabits per second, well, you would send 3 packets out of 4 on the first technology, and 1 packet out of 4 on the second technology. And this is this play limit, this static splitting probability. And actually what we can show quite easily is that if you want to keep using the same splitting probability for each arrival rate, then this is the optimal choice. But actually what we show is that the optimal splitting probability depends on the arrival rate. And actually, one result that we show is that for small arrival rates, so there is some lambda node, such that for arrival rates below this lambda node, it is actually optimal to use one technology, and only for larger arrival rates, it starts to be better to use 2 technologies. And again, we show that experimentally with 2 different Wi-Fi channels. For the first technology, in the 2.4 GHz band, we use a fixed rate. And for the second technology, we have rates varying between these 2 NCS indices. And the optimal splitting looks like that. So this is shown both analytically and experimentally. So for the experimental value, we just run for every splitting probability, and we keep the one that experimentally yields the smallest delays. And we see clearly what we have shown. It clearly depends on the arrival rate, and for small arrival rates, it is better to use only one technology, because the splitting probability is 1. Okay, but the next question is, what impact does it have on delays? Because if, theoretically, the splitting probability is maybe not optimal to always use this pay limit, this optimal splitting probability. But if the difference in the delays is small, clearly it's much simpler to use always the same splitting probability than having to change it for every arrival rate. So now we want to study the impact that it has. And for that, we start with the analytical results. We show the analytical ratio of the delays obtained both with this optimal static probability P lim and with the optimal probability P star. And first, in the very simple case, when the 2 have fixed rate, then we see that the ratio stays actually very close to 1. So what it means is that you do not lose much by using this optimal static probability when the 2 are not time varying. But now if the second technology starts being time varying, so it alternates between 7 megabits per second and 3 megabits per second, we keep the same average service rate, but just modify the variance of the service rate, and we see this huge peak going around 25, 30 megabits per second, and the ratio goes up to 30. So these are analytical results. So what we want to see next is, okay, what about in the real world? Does it happen also in a real experiment? And we still use the same scenario, same setting. And actually, yes, it does happen. Here again, we show the ratio in the delays obtained with the static probability and with the optimal probability. And we see that the ratio can go up to 6 in the analytical case and around 4 in the experimental case. And here again, the difference is really significant. It's 23 milliseconds with a static probability and 6 milliseconds with the optimal probability. And finally, just an example with multi-pass TCP and single-pass TCP. So here again, same parameters. And now single-pass TCP is used only on the first technology, and multi-pass TCP makes the choice of the scheduling. So here we do not choose the splitting probability. Multi-pass TCP does that with the scheduler that it uses. And what we show is actually, again, even though multi-pass TCP and TCP are not optimized for delays, and we do not have this static splitting probability, what we see is the theorem that we have shown. For small arrival rates, TCP tends to do slightly better than multi-pass TCP, and only for larger arrival rates, multi-pass TCP does better in terms of delays. So to sum up this part on multi-pass, we have shown that having two technologies does help, but actually not for small arrival rates. And finding the optimal splitting probability is not an easy task because it actually depends on the arrival rate, even though this has a very strong impact, because when you use the same static probability, there are high differences when the rates are time varying. And now if you have some questions, I'm happy.